Welcome. So, have you ever wondered what's really going on inside an AI when it tackles some crazy complex problem? How does a machine even begin to go from a total mess of data to a clear, logical, and sometimes brilliant solution? Well, today, we're going to pry open that black box and take a look at how an AI actually thinks.
Let's start with something familiar, like a Sudoku puzzle. Now, it might just look like a game, right? But for computer scientists, this is basically a perfect little model for thousands of massive real-world problems. We're talking about everything from scheduling every single flight for an airline to managing the insane logistics for a global shipping company. So how on earth does an AI figure this out?
Now, the first thing you might think is, well, it's a computer. It just guesses. It tries every single combination a billion times a second until something clicks. But nope, that's not it at all. That kind of brute force approach would be wildly inefficient, and for anything more complex than this, it would be literally impossible. The real method is so much smarter.
Here's the secret. At its very core, AI problem solving is all about a structured process of reasoning. Think of it like this. First, you have to learn the alphabet. Then you learn the grammar that connects the letters. And only then can you start writing a story. We're going to follow that exact same path today to really get how an AI solves a puzzle.
Okay, first things first. Before an AI can do any kind of reasoning, it needs a language. It needs a way to describe the world. And just like our language is built from simple letters, the AI's language is built on the most basic idea you can possibly imagine. A statement that is either true or it is false. That's it.
This little nugget of certainty is called an atomic proposition. And for a computer that lives and breathes in ones and zeros, this is absolutely perfect. There's no gray area, no kinda, no maybe. The statement, "the light is on," is either true or it's false. This absolute, black and white certainty is the bedrock that all of its complex thinking is built on.
But a single true or false statement by itself is like a single letter of the alphabet. It's not super useful on its own. To build actual words and sentences, you need grammar. And that's where these logical connectives come in. They're the simple rules like and, or, and not that let the AI chain these simple ideas together to say something way more meaningful, like the light is on and the door is closed.
And here's what that logic looks like in practice. This is a truth table for and it shows you the simple, unbreakable rule. The combined statement P and Q is only, and I mean only true, if both P and Q are true by themselves. If even one of them is false, the whole thing falls apart. This is the kind of rigid, totally predictable foundation that the AI just loves.
Okay, so we've got a language. But for a puzzle like Sudoku, trying to describe every single possibility for every single cell with a true-false statement would be an absolute nightmare. That whole approach is just way too clunky, way too slow. We need a much smarter way to think about the problem, a kind of shortcut. And that brings us to a much, much more powerful idea.
And here it is. This is the big aha moment. Instead of making a ridiculously long list of tedious facts like cell A1 is in a 1, and cell A1 is in a 2, and on, you can just state a few powerful, simple rules like no number can repeat in a row. This is the critical leap. You go from listing all the things that are not allowed to just defining the rules of the game. That, right there, is constraint reasoning.
So why is this leap so important? Well, because the number of possible states, or combinations, explodes incredibly fast. Just 30 simple variables that can be true or false can create over 1 billion different combinations. Checking every single one isn't just slow, it's completely impossible. Constraints let the AI just slash away almost all of that noise from the very beginning.
So, this entire way of thinking actually has a name. It's called a constraint satisfaction problem, or CSP for short. Now that might sound super technical, but it's really just 3 simple pieces. What are the things I can change? Those are the variables. What are my options for each thing? That's their domains. And finally, what are the rules I can't break? Those are the constraints. It's like a universal recipe for turning total chaos into a puzzle that can actually be solved.
But let's be real, the world isn't always as neat and tidy as a Sudoku board. It's messy. And this is where constraint reasoning gets really, really clever, because it understands that not all rules are created equal.
Think about planning a project. A hard constraint is a total deal breaker. The deadline is Friday. If you miss it, you fail. Simple as that. But a soft constraint is more of a nice to have, right? We'd prefer to finish early. This awesome distinction is what lets an AI find not just any solution, but the best possible solution. one that follows all the hard rules while also trying to satisfy as many of the preferences as it can.
All right, so the AI has the rules. It knows the hard lines it can't cross and the soft goals it's aiming for. So how does it actually navigate this incredibly complex web of constraints to find an answer that actually works?
A lot of the time, it uses a really cool process called search and backtrack. So imagine the AI puts a 5 in one of the squares. It doesn't just keep going. It stops right then and there and asks itself, did that move just break any of my rules? If the answer is yes, it doesn't freak out. It intelligently backtracks. It just erases that last move and tries something else. It's not guessing randomly at all. It's systematically exploring different paths and immediately backing out of any dead ends it finds.
And what's so cool is that while this all started with us thinking about a simple puzzle, this exact same logical approach has become the invisible engine running some of the most complicated systems in our modern world.
Seriously, this is not just for games. When an airline has to schedule all of its thousands of flights, or when a massive company plans its shipping routes around the globe, or even when a diagnostic system figures out a complex engine fault, they are all using constraint reasoning. It's the engine that solves the gigantic logistical puzzles that make our world work.
And this quote from our source material really just hits the nail on the head. The true power here comes from focusing on the relationships. It's not about trying to memorize a million different facts. It's about understanding the handful of powerful rules that connect them all together.
So let's take a quick step back and look at the whole journey we just took, from the simplest possible statement all the way to a system that can solve these incredibly tough problems.
I mean, think about it. We started with a simple puzzle. We gave the AI an alphabet to work with, that basic language of true and false. Then, we handed it an amazing toolkit, the whole idea of constraints, so it could define the rules of its world. And with just that, it was able to find these elegant solutions to problems that affect every single one of us.
Which, of course, leaves us with one last, really fascinating question. We've seen this kind of logic master games and logistics and diagnostics. As it gets more and more sophisticated, what's the next great challenge? The next problem that we all thought was impossible that this way of thinking is going to solve for us?